Hello everybody, it's just about time to get started. And before I officially start the actual today's webinar, just a quick few notes on this session. This session is going out live, and by all means, please use the chat box down the side of the screen if you want to communicate with us. And there's an option there if you like. If you don't want the whole world to see your question, then you can mark that as private, so please go ahead and do that. I will have a question and answer session later. Alongside me, I think to that side, is my colleague, Andreas. Andreas is here to moderate and just to monitor everything's happening and working out okay at your end. And he will also monitor the questions that are coming in. If there's any quick questions that he can answer during the session, he will go ahead and do that. So if you want to just say a quick hello, Andreas.
Hello, hope everyone is doing great. Just fire away some questions in the chat if you want something answered quickly. I'll try to help out as well.
Perfect, thank you very much. I'll just go ahead and share my screen and we can get started. Okay, so officially, welcome to the MIRA HDR webinar. This is going to take around about 40-45 minutes, I guess, to run through. I'm going to talk about a few things around the system, what it does, how it does things, and a little bit of theory. So a little bit of agenda for you to start off with. I'm just going to talk about a little bit of an introduction and brief history of the MIRA and where it came from, what it is, etc. I'm just going to talk a little bit about the theory of the 3D data, but to get to the 3D, I need to start back at 1D, go through the 2D and onto the 3D. So a little bit of theory then, and how that system is built up and how that works. To talk a little bit about the MIRA principle, and the MIRA, for those that don't know, stands for MALÅ Imaging Radar Array. It's manufactured by Guideline Geo, who both me and Andreas work for, and MALÅ is the brand of GPRs. We're going to go through the carrier solution and the trailer solutions, what you need for the system to work, the positioning, how it actually monitors and takes its position information, and then go through a little bit of the data acquisition software, which is called the MIRAsoft, and then onto the data processing, which is the R slicer. And then towards the end, we'll go through a question and answer session, and I will pick up any of those questions if they need any explanations that you've popped in the text box that might need a little bit more of an explanation than a quick answer. Okay, so without further ado, I'll get straight in to the history. We're going to start off with a history lesson. Way back in 1999, MALÅ launched the MALÅ, and that was the system that was the computer-aided radar tomography system. And this is one of the first array systems. Actually, it was the first commercially available array system. And you can see it here. This was actually a system that was used in the aftermath of 9/11 in New York City. And it was the Swedish government that purchased that system on behalf of the Swedish people and gave it to the people of New York City, and they used it there for monitoring things like voids and looking for damages to the utilities in the aftermath and in the cleanup process out there. So that was the first use of the system way back in 1999. In 2007. The CART system was first used for archaeology at Uppsala Cathedral in Sweden. That was its first use in archaeology, and that started to open up the doors really in the archaeological world. In 2007, we produced the first MIRA system. This was the next system on from the CART, and it was built around the ProX system, and it had parallel processors, which meant that the speed could be increased drastically. So we saw some improvements in speed and in data processing and sampling of the signal in that. In 2008, this is where I come in, because that's the first time I sat on the system, on the MIRA, and it was launched and it became available as a 16-channel 400 megahertz system. We went on to build some different frequencies from there. We had a couple of different options, 200 megahertz and 1.3 gigahertz, but predominantly the main system was the 400 megahertz. In around 2012, and this came really from two things: customers wanting something a little bit smaller, but we also wanted a system that was nice and portable and that could be shipped around easily for demonstrations, etc. So in 2012, we introduced the Mini Mira. And that was in effect a half-size system of its big brother. And you can see it used there nice on the back of a quad bike. Some of the achievements along this way in this history we can talk about. One of the big ones, and this is one of the first Mira outings, was off down into Austria, and it went off to map out the gladiatorial school in Handcart. And that was in combination with, or in work with, the Ludwig Boltzmann Institute in Austria, and they went on to map extensive areas of Handcart. They also went on to map some other really big places and really big interest of it. They went on to buy multiple systems that were used predominantly around Europe. Stonehenge was another one, and obviously being from England, that's one of my favourites, obviously. And that was a combination of multiple universities: University of Birmingham, Bradford, Ghent, and St Andrews, along with LBI. And they went off to map out not just around that stone structure. Stonehenge itself is a wider landscape. It goes over several hundred hectares or greater than that, that we know of. And they went off to map out these large areas, lots of data collection in an effective way. And they found out lots of interesting things in the broader landscape, which made it quite interesting. One that's a little bit newer and a bit more recent, and you may have seen this in the news recently, the last year or so, and that was the Viking Ship. And that was found by our friends over at NICU, and they used a system to map out a Viking ship. Now, the interesting thing about Viking ships is not that many actually being found in the whole European continent and around Scandinavia particularly. I think there's only about 20 being found, and this was one of them. And the interesting one on this one is recently started the excavations. And this is what the excavation looks like, the archaeological excavation. And if I can just rotate that image around just a little bit so it lines up similar to the photograph, you can actually see some features. In particular, I'm looking at this feature on the edge of the exposed ship. You can see the darkening around that area. That's the difference in the soil composition, and you can see the outline there on the actual data, and it's matching quite nicely. And this is the thing that the system has brought, the resolution. I'm going to talk a bit about the resolution later and things like depth penetration and depth range and that type of thing. But one of the key factors to the Mira is this increased resolution of the measurements, and this has enabled archaeologists to start to interpret features like this in much more greater depth well before the excavation has actually gone ahead. And to an extent, you could almost say that some excavations aren't needed, though they do like to do it to confirm things. But the amount of information that we get from these is quite outstanding. Also, on the more commercial side and in the structural side, and we've been actually out mapping things like airports and that type of infrastructure out there with some bigger and smaller systems. That's a large system on the left hand side. This is out in Asia, and we actually went out on a project. It was a combination project on this one, and it was to map out both a sinkhole formation and also the utilities around the actual airport itself. And here's just an example of some cavity detection across that area. Is a section around the actual runway. So it's about 60 meters wide by something about 40 meters wide by about 60 meters long. And I've taken a cross section. This is a plan view on the left hand side, and I've taken a cross section right across this dark feature here. This is 1.45 meters below ground level, and you can see the formation on the right hand side on the cross section across there. And also another area, this area here was actually a section that was already known, that sinkhole was actually known at that time. So we took some measurements around there just to get a comparison. And a cross-section across this other darker feature in the time slice here, you can actually see quite a distinct change in the ground conditions around that area. That would then lead on to further investigation on that area. So that enables us to cut down and target testing with the system. So they can go in with boreholes or core samples to actually take measurements of the subsoils just to double check what's actually happening down there. Utility-wise, this is an example of some utility data, and you can quite clearly, distinctly see we've got the dark linear features running across the site in different directions. Again, on the airport, quite congested areas, this section, but you can quite clearly see instantly. One of the key things when we're looking at time slices is the ability to almost take away the interpretation of the data, though we still need to do the interpretation, we still need to do the cross sections, but you can instantly see for the person that's operating the system the features, the shape, where the things are going, and the depth of the features, and you can instantly see these particular structures and features in the ground, and that's another obviously key factor new of the system itself. So onto the MIRA HDR. As I said, MIRA stands for MALÅ Imaging Radar Array. HDR is the latest technology, and that is the high dynamic range. It's a system that we produced a number of years ago. It's about 6 years ago since we first introduced the HDR into the Ground Explorer range. And the HDR is based around real-time sampling. It enables us to be able to sample the data at a better level than what we had before. We can gain a greater bandwidth of the data, and that gives us better resolution and better depth penetration from that system, much more than what we were seeing before. So there's improved data quality on this HDR system and the technology. So onto the theory then, just go through a little bit of the 1D, 2D, 3D. I'm just going to start off with a single channel radar system, our standard, this is one of our easy locator antennas. But if we look inside the antenna itself, it's built up of two separate antennas. We have the TX, the transmitter antenna, and we have the RX, which is the receiver, just radio terminology. And what we're going to do with the system, we're going to launch the electrical signal down to the TX antenna, the transmit antenna, and that will generate a pulse of energy in the form of electromagnetic wave, a radio wave in effect. And what I'm going to do just on the section here, this is a recording of what's happening on the receiving antenna. So we'll launch a signal and we start recording, and we're going to measure over time. So we send that signal out. That signal will start to expand outwards in a semicircular fashion because it's a shielded antenna. Just go back one there a second. So that signal is semicircular at this point, and it's starting to expand outwards. You will get some signal traveling between the transmitter and the receiver antenna. That's one of the first things that's going to actually hit the receiving antenna, is this direct wave. And this is what we refer to often as the first arrival, the direct wave, or the air wave. And you can see their response now on the meter, so to speak, on the recording. And that's our first pulse of energy that's actually hitting the receiving antenna. The signal is expanding outwards through the ground. And at some point, that expansion will travel through the soil, and we have a target, and some of that energy will reach that target. Just a split second later, after that air wave that's traveling across from the transmit to receive antenna, we get a little bit of a kick from the ground wave. This section down here is what we refer to as the ground wave, and this section that was traveling directly across was, as I said, the air wave. A small part of the energy that's transmitted out from the TX, a small amount of that energy has reached the target, and where we get a change of electrical properties between two materials, that change of electrical properties will cause a reflection in that energy. So some of that reflection will be bounced back. It's an echo, in effect, from that target. So as time goes on, that will start to radiate backwards towards the surface, and eventually nothing happened on the receive antenna, so it's a dead flat line until that point where we get that signal returning back to the receiving antenna, and we get a small response on that trace. And we actually refer to that quite often as the wiggle trace. Nothing too technical there, it's a trace and it's wiggling. So that's our one recording, that's one shot of signal into the ground. And what we do with the radar, we move the radar forward, and it's going to take measurements at intervals, at set intervals, along where we're pulling or pushing the radar system. And it's going to take these measurements one after the other. And you would effectively, if we did do that and looked at all these wiggle traces side by side, it can get quite complex. It can look quite difficult to interpret the data when we look at these wiggle traces. Sometimes we need to look at them to interpret the data, but what we're initially going to do, we're going to convert that into an image, and that's where we typically convert that into a form of grayscales. And this is effectively, the center would give us a gray color. To the right on this grayscale plot, it will go towards white, and to the left it goes towards the black. So where you get a pulse going to the right, that would create a block of white data in effect, or lighter gray, depending on the size or the amplitude of that signal. So all these measurements are stacked up together, and it's going to create this, which we refer to as the radargram. We can see some features and things happening in that radargram. And in effect, the wiggle trace is our 1D measurement, and from that we can actually gauge a depth value. Later we need to do some conversions, because at this stage it's a measurement of time, but we can convert that into depth a little bit later. The radargram is referred to as a 2D measurement because we've got the 2 dimensions now, so we've got distance and effectively time down the vertical axis, or depth, whichever we look at it. And that's effectively giving us our X measurement. So we've got our X measurement and we've got our Z measurement. We're missing one. That's where I'm going to come on to that in a second. So there we go. That's 1D through to 2D. And we do actually still use 2D quite a lot. A lot of people want to go to the 3D, but even though when we're working with 3D measurements, quite often we go back to 2D to interpret the data. So for those people that are wanting to get to 3D, don't discard the 2D quickly. It's got useful information in there that we use quite often. So the 3D is nice, it looks pretty, but don't discard that 2D too quickly. So how do we get that 3D? So the principle is that we're going to take one line of data in effect, but not just one, multiple lines of data, or multiple profiles, and we're going to stack these together side by side, and we're going to generate a cube. And when we generate a cube, this gives us the ability to be able to look across this horizontal plane around this cube of data, and we can generate these horizontal slices through the data, and these are referred to either depth slices or time slices, depending on who you talk to. They quite typically refer to them as the time slice, because we're looking down through time. When we convert that to depth, we're looking down through depth, obviously, and in effect what we can do here, we can start to peel the ground away and start to look deeper and deeper down into the soil. And this, in effect, is now giving my Y measurement across the axis. So before we had our Z value, across this edge we had the X, and now we've got our Y measurement, and that is our 3D measurement. That's a critical thing here. We can start to put cubes and things and make it look all really fancy, but in effect the 3D measurement is this horizontal plane, this plan view from above, and from that we can generate these time slices. I'm just going to run a quick video here. So we're going to start at the top, run down, look through these slices sequentially, and we can generate some nice images like this. And this is looking down from top to bottom. Now, the interesting thing with this data here, the resolution doesn't look very good, because this isn't actually mirror data at this point. This is just some standard single channel data, some of these collected lines of data at 1/4 meter profile spacing line spacing. So it's relatively coarse, is this. But you can see the principle here of looking from that top to bottom. It's just cycling through. And it's going to the top and then running through to the bottom and back through again. You can see some features in there. I can see some rectilinear features, typically from buildings or archaeological buildings. I can also see a utility or certainly a long linear feature running across the data, just around about that position there. It's interesting, there's maybe a footpath or something running across there close to the surface. And like so you can see those rectilinear features in that data set. It's a nice little bit of data there, but we can make that look better. And we can make that look better by increasing the resolution of that data. So how do we do that? Well, we're going to collect lots of lines of data, what we refer to as a swath. So the whole width of one antenna is the swath. And to get that high resolution, it's mainly dependent on identical antenna signatures, because we've got multiple antennas inside the system. They have to be all reading identically. Very, very sort of similar measurements. And the center frequency that we're going to use is quite critical. But the biggest factor here is the distance between the channels, or the data density. And here the thing with the new system, with the new MIRA HDR, the spacing between the channels is 6.5 centimeters. That is the highest data channel density on the market at that frequency. I'll go through the frequencies and things like that in a few slides' time. But it's really tight. So effectively, it's almost like taking a single channel, a signal channel antenna, walking down the road or over the field, moving over 6.5 centimeters, walking back down again. And that's going to increase that resolution. That's what's going to give us those nice, beautiful images. So the MIRA HDR system is there to perform high resolution 3D mapping of the ground, and it's a most cost-effective GPR solution for collecting quality data over large areas. Here's a key thing: we're going to collect huge volumes very quickly with the system at this high resolution, down to a few meters depth. Now, with GPR, we can look quite deep, but when it comes to 3D and that type of measurement, we do have some restrictions on what sort of depth we're going to go to. But in effect, what the system's going to give us here is that high resolution 3D mapping as complete GPR solution. So if we look at the components of this system itself, the MIRA system, what's it include? Well, we've got the actual antenna array. This is the box in the center here with a nice big orange MALÅ, or for our friends in Sweden and Scandinavia, I should be pronouncing that MALÅ. But this is the antenna system here, the array, and we'll have a look inside that in a second. We must have an accurate positioning system. We are collecting data and we need some very accurate positioning in that data. And we need to get down to really centimeter accuracy with that. So I'll just touch on the accurate position system and what we need for that in a second. I've got a slide on that. We need some form of carrier or trailer solution. It's a larger system. You can hand push it, like what the setup is here. That will slow down your data collection. Sometimes that's needed because you may not be able to get a vehicle into the place where you're data collecting. So there is possibilities to use it in the hand collection. That will slow you down a little bit. And also we need a vehicle ideally, because it's all about collecting that data. And I'm going to talk about the speed of data collection as well in a second, which is a critical thing and an important thing on the new system. We need some form of computer, an acquisition computer, and the software to collect that data. When it comes to the computer, I will definitely recommend a ruggedized laptop or tablet. For that, you can use a tablet or laptop, but definitely a rugged version of those more tougher laptops. Try not to mention a name there, obviously. We need some post-processing and interpretation software as well. So let's have a look inside that antenna from above. This is the box. So if I peel back the lid of the box, you'll see there's a number of TX transmitters, RXs, receivers across the array. And there's actually a very unique way of arranging these antennas in here. And you see this slightly overlapping. we have 12 receivers and 11 transmitters. And what we're going to do is we're going to communicate from the TX antenna through to the first receive antenna. Then we're going to fire the signal again from that first antenna, first TX antenna. We're going to fire it through to the receiving antenna and sequentially down the bank of antennas. So this overlap is actually quite important, because if I put the conventional way of a GPR antenna having a receiving antenna and the TX antenna right behind it, the spacing between the channels is increased. And this overlapping that we're doing here enables us to take tighter measurement points across the array. And this is where we get the very tight channel spacing. It's quite a unique way of overlapping the antennas on the array itself. But what that enables us to do is give 100% coverage at very tight spacing, like so. Just a few values here for you. The data coverage at the surface, that is, the signal will expand out as we transmit to the ground. But the data coverage is 136.5 centimeters, almost 4.5 feet. And that's from channel to channel. The box is a little bit, just slightly wider. It's about 171 centimeters from edge to edge. We can actually have a maximum of 132 data channels using the 11 transmits and 12 receivers. I'm just going to show you what that is in a second, what I mean by that. As I've highlighted already, it's 6.5 centimeters at 500 megahertz. That's the central frequency. But do remember, when we will look at different frequency, different antennas, it's a high dynamic range antenna, so we've got extra bandwidth from that 500 megahertz. But the 500 megahertz is a real sweet spot when it comes to, first of all, arrays, but also for utility and archaeology. I'm going to talk about the applications a little bit later on what we're going to use it on and what it's most effective on. And as I've highlighted already, it's the best data point density in the market. Data collection, the speed of data collection is highway speed. And what do I mean by highway speed? Well, it's on two factors really when it comes to the highway speed. You've got the speed limit of the road, what the legal limit of the speed of the road allows you to do. So let's say on a 50 kilometer per hour road, we can collect data at that speed with this system at point interval or trace interval or measurement interval of 6.5 centimeters. So we've got the data channel spacing of 6.5, and we're going to collect data at 6.5 centimeters in line. We can increase or decrease that depending on the application. But at 6.5 centimeters measurement interval, we can run this at highway speed if the road allows us to do that. And when I say that, I'm also talking about the surface of the road as well. If I've got a ploughed field as an example, I won't be able to drive across that at 100 kilometers per hour. Obviously, it's not physically possible to do that. And it can be the same for some roads, some construction roads. If there's lots of potholes, humps and bumps, that's going to slow you down. So even though the speed limit may allow you to go 50 kilometers per hour, we can't physically do that because of the condition of the road. But most roads, apart from the Autobahn, up to 100 kilometers per hour, we can run this system at that speed and collect data at that speed. So it's super fast, and this is one of the key things with the HDR technology, is the speed of data collection. So we can run this really, really quickly if the road allows you to do that, if the speed limit allows you to do that. So that's what I mean by highway speed, and we can run that effectively up to the speed limit. And obviously, you've got to take into consideration the trailer as well. That sometimes regulation-wise will mean you have to drive a little bit slow because the trailer is actually regulated to a certain speed limit. So that's why we don't publish the figures here too much. We just refer to it as highway speed. So what is a data channel? What I mentioned just a second ago. But as I said initially, we're going to fire from the first transmitter to the first receiver. That's one data channel. And then we're going to sequentially run down the data, down the bank of channels to collect the data. Here we've got 5 data channels. If I continue, what I can do, typically that first array, that first measurement there, running down the bank is the standard setup. But what we can do now is actually fire from the first transmitter to the first receiver, and then the second, the third, and the fourth, so on and so forth. That enables me then to take 12 data channels from that one transmit antenna. This is a measurement that we can perform, and some people do this, and it's referred to as a CMP/OR measurement. It's a common offset measurement. This enables you to do some other things, not just utility and archaeology. We can start to look at moisture mapping of the subsurface, and this can be used for analysing road construction and defects in roads, particularly. So that's 12 channels there, and if I then run from the second and the third transmit and transmit to all the receiving antennas sequentially, I build up this bank of data, and that will give me my 132 data channels. Now, it's impossible for me to put all the data points across there, so I've just drawn a white line from left to right. There's so many of them, but this enables us to take all these 132 data channels just from those antennas that we have in the array right there. Okay, so what do we need then to operate the system? We need a carrier or a trailer solution. Three basic systems that we have. We have the Handcart, a hand-pushed cart system. What I will say on that one though, because of the size of the system, it's really only suitable for hard standing surfaces. So I'm talking about asphalt, tarmac, and or concrete surfaces on that one. You'd find it quite difficult to hand push that over a field, arable field or grassed area, etc. We can front mount on vehicles, and we can also use the rear mounted road trailer on the back. Here's an image of one of the road trailers that we have, and on here you see the antenna in the center. We have a number of electrically operated winches. So what it enables you to do is remotely raise or lower the antenna. So if I'm driving to the site, I can raise that antenna up and run the system to the measurement area, to the site or the area of investigation. Now I can drop the antenna down and then start to take my measurements on there. So that's the trailer option. You can front mount, and typically people have mounted this on an ATV, these side-by-side vehicles, and quite often these will have either hydraulic lifters at the front or an electrical winch, and that enables you to lift and lower the antenna, again, for maneuvering around the site, and then once you get into position, drop the antenna down and collect your data. Quite an effective way of collecting data. And some of these ATVs now are getting some decent speed on those, maybe 50 kilometers per hour, so you can get some speed up on those. And like I said initially, there's the handcart system. The antenna in the handcart option. You can actually put that in a trailer configuration as well. So if you want to pull that behind something like a quad bike or even behind the ATV, you can attach an A-frame to that and tow that behind something like a quad bike or something similar. All righty. Onto the positioning then, accurate positioning system that we required from that. What do we mean by that? Well, we need at least an RTK GPS. RTK typically will give us sub-centimeter measurements, typically. It really depends where you're working and the infrastructure above the ground. Where RTK isn't working very well, the GPS, then we may want to use something like a robotic total station, and that will track a prism on top of the antenna, and that will give us our positioning, and that information from that positioning is stamped into the data. And one of the critical things with GPS and robotic total station is we get a little bit of a lag in the system. And this is something that, while some of the older systems that worked a little bit slower, it wasn't that critical. With these new systems, if we're driving at 50, 60, 70 kilometers per hour, and these have even just a few milliseconds latency or lag in the system from the information getting from the GPS through onto the GPR, it causes an issue. So what we've actually done with the system to overcome this is have an inbuilt GPS module inside the antenna itself, inside the GPR antenna, and we use this for synchronization, and we're going to get this time signal from that internal GPS into the GPR data, in effect time stamping, and that enables us to synchronize the information coming in from the total station or GPS. And this is critical for that accurate data collection at speed. It's really important. So that's what I mean by accurate positioning system, just the bog standard GPS or even just the differential GPS that gives you meter accuracy is not really good enough for this system. It's gonna mess up the data collection. The information is not going to be good. So it's really important that you get good quality accuracy from the position itself. So on to the acquisition software. And I'm running through this pretty quickly. I don't want to go on too long with all this stuff with you. Just want to keep it short and sweet. There's lots more information on our website. I'll show you the website a little bit later. If you find some information there, you can always contact us later as well for more information. But the data collection, the acquisition software itself is the MIRAsoft HDR. And that enables us on a few things. It's a completely new development is the MIRAsoft HDR. It has a map function with swath coverage. I'm going to give you a quick demonstration of that in a second. I'm just going to switch over to a demo of the software. But we have a sitemap, a plan view. That can be downloaded. It can be offline, online, your option. And we can see where we've been when we've been data collecting. And that's quite critical for data collection. You need to know where you've been and look at the coverage. It can aid a little bit on the navigation as well. Very simple tools and settings in there. Again, run through that with you. We have this max amplitude plot on the right-hand side. This is across the whole swath. And as you're collecting data, you can see images and features underneath you as you're data collecting. And it's almost effective as a time slice across a section of the data. And also we have the cross-sectional view as well on the bottom left-hand side. So we can look at the data coming in and look at the quality of that data. But we've very much made it user-friendly, very much like all our other software, and easy to set up. Okay, you can, when it comes to data processing, I'll go through that in a second, but let me just switch to the actual software itself. This is the MIRAsoft HDR, and this is a demo data. So you see the antenna moving across here. Let me just go back to the beginning on this one. We've got the menu options down here. We can set a new project in the top left-hand corner there. We have the settings in here. We need to change maybe some of the GPS settings and that type of thing. We can change the stacks. We can change the time window, the depth of the actual depth that we're recording. Trigger options here. We can change it distance and time. So different settings there for the measurements. We've got the positioning settings. This is where we tell it where we're looking at GPS or RTK. We can set the COM ports up on this one, and we can download the map if needed. The advanced settings. This is just for the signal positioning, the geometry settings, and the power settings. We'll look at all the tracers and the point of where the zero value is for the first arrival. And then onto the measurement options. A few different things we can look down here. We can just have a look at the site view, so we can expand the map out to full screen if we want. We can just look at the top view. We can look at just the profile view if you wish to do that. And by the way, down the right-hand side here, we can select the different channels, so you can have a look at in 2D across any of the channels across there. And then we have the expert view, and that's all three of those views all set up together, all in one. And if I just hit the record button down here, or the start measurement button, we start to take a measurement. It will just kick in a second. We'll see the data collection as we go through that. There we go. So you can see that the max amplitude plot on the right-hand side there. There's nothing too much happening in the data here, but you start passing through, and you can see the building up of the 2D. And like I said, you can run down any of the channels you wish at any time and look at the different channels across the area. And we can see the area being painted. It's almost like taking a big paintbrush behind the antenna itself, and you can see where you're moving and see where you've been. And that, like I say, enables and aids your navigation. We have a speed indicator down the left-hand side here. As you increase your speed, the bar graph will start to rise up. It goes from green to amber to red, and that will give an indication that when you're reaching maximum velocity of the whole system, as it's collecting the data, the load on the system, in effect, is reaching maximum. So then you just back off a fraction, And it also gives you the kilometre per hour value there in the bottom left-hand corner. So a few different things on there that you can monitor as you're data collecting. We can just hit the button down at the bottom here. We can change the gain of the profile view. We can change the gain of the top view. Just these slider bars, just easy to use slider bars to increase and decrease. We can enable the bandpass filtering quite quickly, background removal. This is just for the displayed data. The collected data is saved in raw format. And a few other things you can change on the vertical axis and the measurement units, meters, feet, time, distance, that type of thing. So very quick, very easy to use, very effective, simplified, just for the data collection itself. So once we've collected the data, then we're going to export that information out, and we need to post-process that data. And we have two options when it comes to data interpretation, data processing. The first option is our MALÅ slicer software, and that's designed for just the MIRA data. And we've done that for a big reason, is that we can dedicate it to just processing that data. That makes it quick and efficient and easier to use. You can, for those people that want more in-depth, more complex software, you can use GPR Slice. There is the MIRA module that you can bolt onto the GPR Slice. So there's a couple of different options there if you want to use a third-party software or our own. And if we look at the R-Slicer software itself, here's a small section of data. This is the MIRA HDR data. This is one of my colleagues who likes to add a little bit of color into his plot, into his scales. He's not a big fan of gray scales, but he likes to add a little bit of color in there. And this is you can see down the right-hand side here, we've got a number of processing steps. There's a couple of different routines that is run here for processing. And what I'm going to do now is I'm just going to run down the time slices, and you can see on this box down here, the section that's highlighted there is the slice number. We have the time measurement of that time slice, and then the Z value or the depth value if we've calculated the velocity correctly. And what we do is just run down in these different time slices in different depths, and you're going to see the utilities in this case appearing and disappearing as I go down. And you can see the quality and the resolution of this data. And some interesting things that kick in as I get a little bit deeper down to the depth, just go about 0.6, near 0.7 there, and get down to these values down here, and you'll see these nice 4 utilities running across the site. They're meeting up against this main line here. We've got 4 service connections going off to the side. The interesting factor here is looking at the depth. I'm getting down to about 0.8 of a meter deep here. And if I just zoom in there just a little bit and just take a measurement across these 4 utilities, we've actually got a measurement of about 0.58 of a meter, maybe 0.6 of a meter there, just about. At a depth of 0.8 meters deep, this is indicating, for those that really know about GPRs and noise systems, this is showing the effectiveness and resolution of these of this system, and to get that sort of resolution at that depth is quite an achievement with GPR, and that's just a quick result, quick effect look at the actual quality of the data itself. So what's the ideal circumstances for the MIRA HDR? I would generally say it's open and flat areas. If you've got ploughed fields, that's going to slow you down. It's not a problem, but it's going to slow you down. Wooded areas, obviously, it's not going to be that effective. You go into the forest, in the woods, etc. You're going to have lots of gaps in the data, and that's going to lose the effectiveness of this 3D ability. Much better to just drop back to the 2D options there, 2D antenna system if you're going into the forest, etc. Relatively non-conductive soil, and that just goes without saying really with GPR. It says no clay, no saline water infiltration. Clay, we do go out and take measurements on clay quite often, and it's down to the water content typically that's going to make it more conductive. Dry clay is relatively okay, but obviously you've got to watch out for the clay. That's the one that's going to reduce the depth penetration and the effectiveness. It's the conductivity that's going to impede that signal. So larger areas, really, we're going to use the system for that high resolution 3D imaging. That's where we're going to mainly use it. And the ideal targets are point objects and linear features, linear objects. If you're moving into geology, it's probably not the best system to use for that. You're typically looking for deeper objects. Ideally, we're looking at depth targets down to about 2 to 3 meters with the system. Once we start going beyond 2 meters, you start to lose the effectiveness of the 3D, the high resolution 3D. You start to lose the high resolution in a way when you start going beyond that. So we have actually limited the time window on the MIRA system to 5 meters. The GPS signal can go beyond that, but the effectiveness of this high resolution just is lost beyond 5 meters. So we've restricted it to that sort of range. The ideal application areas then is utility mapping, typically. Like I say, that large data collection, large areas very quickly and very effectively. Archaeological mapping, you've seen the data there of what we can get, even from the old system. If you think the old system was pretty good, have a look at the new system. That resolution is improved quite considerably. Road mapping, so we're talking about like the road measurements for the structural information and maybe things like the moisture content and the quality of the road itself. And that lends on then to airports and runways and that sort of area as well. And particularly with airports, that's important because quite typically when we're collecting data on airports, you are really restricted to certain time windows. Maybe when the flights aren't coming in and out, maybe in the middle of the night, you may only have a couple of hours to get out there, get the data collected and back in again. And this is where it's really going to perform and in its best way. Cavity detection, going to be pretty good at that. Near surface cavity detection, obviously. So really, any large area where you need high resolution for that data collection. Less ideal areas, deeper targets, like I said, beyond 5 meters. This system's probably not that beneficial for that sort of area. We will be very honest with you. Both Andreas and I work in the tech support department. We are application engineers, and you can drop us a line at any point. And if you've got any questions, we will be honest with you and we will tell you if we think the system's suitable or not, and maybe give some recommendations for other equipment if we have that available. So most geological applications looking for the layers instead of objects, and deeper objects, typically with geology, it's probably a little less ideal than the ones on the left-hand side. So some of the highlighted features then, just getting through to the end of the sessions now. So the MIRA HDR enables fast and effective mapping of that subsurface at highway speed. So we can get out there and collect that data really quickly, really effectively, productivity up and effectiveness. We can we can get up to about 60 hectares per day. That's a lot of data collection. It's a huge amount of data collection when you think about the channel spacing and the inline measurement of that data, the amount of data we're collecting over there. So up to 60 hectares per day. That time synchronization is quite important, like I said earlier, for that accurate positioning. That's a nice feature. And best resolution enabling more accurate mapping. That's where it's going to provide for you. And like I said earlier, that offers the highest resolution, the clearest data available. So we have that. To get that, remember, to get that, we need that really tight channel spacing. And we have the smallest data channel spacing on the market at that frequency. And we've got the high dynamic range that gives us low noise, which gives us better depth penetration and better resolution. And that's based around that real-time sampling. That's the key factor here to give that velocity, the speed of data collection. And don't forget, that's all based around the 32-bit data output from the system. That is from the data sampling point of view, not 32-bit on your PC. I would definitely say it's probably one of the most user-friendly 3D radar solutions on the market, and that's one of the key things when we're starting to build the systems. And you look at all our different GPR solutions that we have, one of the key things is to make it user-friendly as possible. And we've looked at input from the users quite considerably with this. So we've opened up, asked people what they think, what they need, and gone out. Apologies for that. We have different carrying solutions to cater for different needs. And it's a real field-worthy solution. It's built on proven technology, and it's based on long experience. We've been manufacturing GPRs for a long time now, for over 30 years, and we have a lot of experience, and that's what the system's built around. We've got over 23 years round actual array manufacturing, and that's a lot of experience, and we've put all that experience into this system itself to make it, like I said, the most cost-effective system. And don't forget, it's built on that well-known Swedish manufactured GPR technology, which is well known for its quality. We've got systems that are out there that are getting on now for, like I say, over 20, getting on for 30 years old, and people are still using them. It's a real well-built, well-engineered system for you. Okay, there's my email, mike.langton@guidelinegeo.com, and also Andreas's email there as well. And there's our website at the bottom. If you think of any questions later, you can drop me or Andreas an email at any point. If you go onto our website, there is an option there to put an inquiry in via a ticketed system that goes in, and we have a few application engineers and support engineers that will answer your questions from a technical point of view. And also you can contact our sales through the website as well if you're wanting to have a look at the system and the demonstration, etc. So I will just go back to the questions. So at this point, we will go through anything. I'm just going to pull Andreas back in if he's still with us, and see if we've got any questions outstanding.
Yeah, we have a few questions that has come in. I think it's I think I've managed to answer most of them. It was regarding depth penetration of the MIRA. I think you touched upon that as well in the presentation. We also had a question on data processing times, if you're comparing the easy locator wide range or the MIRA, and that would obviously depend on what kind of a single channel survey you're doing, or dual channel in this case. Mm-hmm. If you're marking out as you go, obviously, then data processing times will be very small. If you go on to do processing for the single channel systems, then I would say that we have a really attractive software in our slicer that is really, really fast. So data processing time is not really an issue.
I think when it comes to things like, you look at, either easy locator, whether you look at the single channel option or the dual channel option, the wide range or the MIRA system, they are two different systems completely. And quite often, sometimes you may be mapping a small area, and to actually deploy the large scale GPR on that site is not going to be effective. You can go out there with the single channel and collect your data quickly, rapidly, probably, potentially, even before I've set up the big system. So there may be times where you still need to fall back to something like an easy locator to look for utilities. Quite often, people may have both systems. So if they want to collect the large areas, they would utilize the MIRA system and use the single channel for the smaller areas. And some of the larger utility mapping companies may have a number of single channel or dual channel systems, and maybe one or two of the MIRA system. So I think they're going to work side by side. They're not going to replace each other. It really depends what you're doing, where you're working, and the size of the area. If you've got hectares of data to collect, then these locator would take you a long time, days, if not weeks, to collect hectares of data. And that's where the Mira will come in and just mop that up in a matter of hours or days, depending on the site. So it really depends what you're working on, that one, and the area. Any others outstanding? Any others as well need to answer, Andreas?
Some questions on how to integrate Mira with GPS or robotic total stations. Yeah, most of the systems that output an NMEA string is possible to connect to the system.
Yep.
And that goes for, I think, if you're going for a total station, that would output a pseudo NMEA string, but it's for most major brands possible to output that through a cable, and that is possible to integrate with the system, as well as on the GPS side.
Okay. Any other questions there? Or have we answered them all?
I don't think we have anything that we haven't touched upon already, as far as I can see. Good.
Excellent. Okay. Well, what we'll do is we'll finish the webinar just in a few moments. I will just, once I've finished the webinar, the chat box, the chat options will stay open for you. So even though I've stopped the actual presentation itself, I'll just hang around for a couple of minutes to make sure there's not any more questions coming in. And like I said, you can just drop us an email at any point via the different options there on the screen. But I'd just like to take this opportunity to say thank you very much for attending. We appreciate your time, and stay safe, everybody. Have a nice day, and we will see you soon. Keep an eye out for the postings. We have got some more webinars coming up very shortly in the next few weeks, so keep an eye out for those, and we will see you soon. Thank you very much.
Thank you.